Hello everyone, I'm Eishi Arima, a research associate in this center. In this presentation, I'll be talking about software-hardware optimizations for next generation supercomputing. Okay, in the first place, let me talk about the HPC research landscape and where our focus is on. So there are lots of objectives when we build or optimizing supercomputers. The performance is a king, but the others are constraints for the performance, such as energy efficiency, resilience, productivity, security, cost, whatever. In this talk, we are focused on the performance and the energy efficiency. And if you look at the computing system stack from devices to application, our focus is from microarchitecture to programming models, programming languages, especially we consider the interactions across the stack. And we should also look at the state-of-the-art promising technologies for the future. And due to the space limitation, I could not list everything here. There are lots of other nice technologies. And our focus is basically power and data management and heterogeneity based on new hardware devices such as non-volatile RAMs and 3D stacking. And our first research topic is about footprint-aware power capping. This is a power management approach, and the background is hierarchical power management will be a must for future power-constrained supercomputers. That usually consists of global power control part and local control part. So global control part basically tries to distribute the power budget to all compute nodes, and on each compute node, it tries to optimize the power budget allocation to each component within the node by exploiting the allocated power budget by the global controller power scheduler. And our focus is on local control part. And our insight here is optimal power allocation to components. Here can change considerably when we scale the problem size of application, especially on hybrid memory system. This is one example that consists of DRAM plus NVRAM. And suppose we execute one application, we usually test various problems, and which could change the data size of this application, and then that changes the optimal power allocation to this component, CPU, DRAM, and VRAM. And first contribution in this study is mathematical part, program formulation and performance modeling. And the second contribution is a profile-based software framework that consists of efficient calibration method that determine the coefficients in the performance model efficiently using the benchmarks, and also the power allocation algorithm that is also important, and that is a hill climbing based algorithm. And the result is quite promising for various cases. And as a next step, we are considering the scheduler-based approach. And the objective is we are to develop a job or a power scheduler using the insights gained through this power capping work, such as footprint awareness, performance prediction, performance modeling, and system design. And that is supported by a grant. And our focus is especially co-location or co-scheduling that tries to launch multiple different application or jobs within a node to exploit the throughput or energy efficiency. One is footprint-aware co-scheduling. That is the initial idea was presented at the ICPP poster session, and this is still ongoing work. And also another promising topic is IO-aware co-scheduling. That is ongoing work, and will be an international collaboration. And we also conducted large-scale power evaluation, especially using the supercomputer Fugaku, that is a world fastest supercomputer ever at this point, autumn 2020. And large-scale power evaluation we did using over 20K nodes. That is a supercomputer Fugaku, and that is powered by the A64FX processor. Actually, the processor has various good power control features, and we focus on some of them, such as floating point pipeline scaling, and DVFS also, and also the core count scaling. And we are also evaluating the future of HPC microprocessors by extending the existing performance and power simulators that is used for the development of the Fugaku system. That is also ongoing work. Please stay tuned. And we are also working on some data management techniques. One is pattern-aware staging. This is based on the open question, how can we exploit both the high bandwidth and the large capacity at the same time on a hybrid memory system such as HBM plus DDR4 or DRAM plus NVRAM such as Optane-DIMM. And our observation in the access pattern matters when we try to decide whether or not to move a chunk of data on the memory. Especially, more specifically, we consider performance benefit versus data movement overhead. If the benefit is larger than the overhead, we should move the data, otherwise not. And it highly depends on the access pattern according to our observation using a real system. And based on the observation, we proposed a technique lightweight software mechanism that is called pattern-aware staging that can be automated by source-to-source compilers. This is the overview of how it works. So the original code, left figure is the original code or original loop that is transformed into the right diagram. And this part is tries to detect the pattern and decide whether or not to move the chunk. And this part consists of three things. First one is sampling. That is based on a conventional helper threading-based approach, inspired by them to acquire the address sequence. And based on the acquired addresses, we detect the characterized access pattern by using the Bloom filter-based approach. And we also proposed to introduce a criterion to decide whether or not to move the target chunk. And the evaluation result was quite good. And we also proposed a hardware cache management, hardware-based approach, caching. And the background is significant cache conflicts among different types of cache lines on lower level caches. And here we focus on data instructions and page table entries and the significant conflict. Let me explain this with this figure. This is an incoming access request. Firstly, virtual address is given that is translated into physical address on the TLB. In case of hit, data access is conducted, but in case of miss, page table walk is incurred to fetch the necessary physical page address, and that is used for the following data access. And at the same time, instruction fetch is conducted, and in case of L1 instruction cache miss, the lower level caches access. that can potentially cause conflict on this structure. And this is becoming more and more serious. First reason is PT accesses are becoming more and more critical because modern work will use larger and larger data with more and more irregular accesses, and in general, and also code footprints are increasing, especially for modern server workloads. So why don't we set appropriate allocation priorities on the cache structure? And this is a summary of what we proposed in this study. We firstly augment functionality to set a unique priority to each class. And then we partition a module that is used for estimating the reuseness behavior of each incoming cache line by using. That is basically a history of victims. Like this way. I will not talk about the details of that. And we also provide a control system to optimize the priorities and partitions. Those are basically the parameters, and we use a feedback control approach to optimize the parameters at runtime automatically by using the stats of the history. And the evaluation result is quite promising. And let me conclude this talk. We are aiming at providing various insights that can potentially change the way of supercomputing, and the approaches are based on software and hardware, and sometimes those are interactive and cooperative. And these are related publications, and if you are interested in the details of what I presented here, please check those papers. And for some of these papers, conference talks are available on YouTube. Please check them as well. And these are the speaker's contact info while he is belong to the university. And if you have any questions, please contact to this email address. Okay, that's it. Thank you very much for watching.